Have you ever just stopped and really thought about what it means for something to be, well, moving? It seems so obvious, right? A bird flies, a car drives, easy peasy. But when you really start to dig in, you find that this simple idea of motion is actually one of the coolest puzzles in all of science. So, let's start to unravel it, shall we?
Okay, do me a favor. Take a look at the walls around you. They seem pretty solid, right? Perfectly still. But here's a thought that might just bend your brain a little. You and this entire room are on a planet that's spinning at over 1,000 miles an hour while also rocketing through space around the sun. So, let me ask you again. Are those walls really still? This is exactly where our whole exploration begins.
You know, this idea that motion is relative is literally everywhere. Just picture yourself on a bus. From your seat, the person across the aisle is just sitting there, not moving at all. But to someone standing on the sidewalk watching you go by, both of you are zooming past. So who's right? Well, here's the wild part. You both are. It all just depends on your point of view, your frame of reference.
Okay, so if everything is relative, that kind of throws a wrench in things, doesn't it? How can we possibly study motion if we can't even agree on what's moving and what's standing still? It feels like we're stuck before we even start. But don't you worry. Physicists came up with a really clever way around this.
To solve this whole "it depends on your point of view" problem, scientists came up with a simple but totally brilliant idea: the reference point. You can think of it like dropping a pin on a map. It's one fixed spot that everyone agrees is the starting line. That way, we can all measure an object's journey from the exact same place.
All right, we've got our pin on the map. Now we can start tracking things. But it turns out there's more than one way to describe how far something has gone. This brings us to two super important concepts: distance and displacement. They sound similar, but they tell very different stories.
Let's imagine a little object on an adventure. It starts at its home base, travels 60 kilometers in one direction, and then, for whatever reason, it turns around and comes back 35 kilometers. So the big question is, how far did it actually travel?
So first, let's talk about distance. Distance is literally the total ground you covered. Think of it like a pedometer. It just counts every single step. It doesn't care if you're walking in circles or a straight line. So for our little object, the distance is just simple math. 60 kilometers out plus 35 kilometers back. That's 95 kilometers in total.
But then there's displacement. Displacement couldn't care less about the winding path you took. It's all about the shortcut. It's the straight line from your starting point to your ending point. So for our object, even though it traveled 95 kilometers, its final displacement is only 25 kilometers from where it began.
And this quote right here, this is the key. It really gets to the heart of it. Just imagine running one full lap around a track. Your distance is 400 meters, for sure. But because you ended up exactly where you started, your displacement is a big fat zero. It's the perfect example of how you can put in a ton of effort and cover a lot of ground, but technically not go anywhere at all.
Okay, so we've got a handle on measuring the path of a journey. But what about how fast that journey happens? This is where our next two key ideas come into play: speed and velocity. Now, in everyday life, we use these words interchangeably, but in physics, they are definitely not the same thing.
Right. So think of speed as the number on your car's speedometer. It just tells you how fast you're going, 50 kilometers per hour. That's it. Velocity, though, is way smarter. It's like your GPS. It tells you you're going 50 kilometers per hour north. It has both speed and direction. It's the difference between just moving and moving with intent.
To really see the difference between speed and velocity in action, let's dive in, pun intended, with a fantastic example. Let's meet Usha. She's a swimmer, and she's about to show us just how crucial that little detail of direction really is.
So Usha's workout is pretty simple. She swims 90 meters to the far end of the pool, touches the wall, and immediately swims 90 meters right back to where she started. The whole trip, all 180 meters of it, takes her exactly 60 seconds. Now for the puzzle. What's her average speed and what's her average velocity?
First up, let's calculate her speed. This part is easy enough. We just take the total distance she swam and divide it by the time it took. So that's 180 meters divided by 60 seconds, which gives us an average speed of 3 meters per second. Not bad.
Okay, but what about her velocity? Now remember, velocity cares about displacement, the distance from start to finish. And where did Usha finish? Right back where she started. Her displacement is 0, so her average velocity is, you got it, 0 meters per second. It's kind of mind-blowing, right? She was swimming her heart out, but her overall velocity was nothing.
So far, we've been dealing with things moving at a nice, steady pace. But the real world isn't usually like that, is it? We speed up, we slow down, like when you're in stop-and-go traffic. So how do we describe that kind of changing motion?
There is a word for that, and it's acceleration. Now, most of us think acceleration just means hitting the gas pedal, but in physics, it's any change in velocity. So speeding up is acceleration, but hitting the brakes and slowing down is also a type of acceleration. It's the rate at which your velocity itself is changing.
Let's follow this guy, Rahul, on his bike. He starts from a dead stop and gets up to speed. That's a change in velocity, so it's a positive acceleration. A little while later, he hits the brakes to slow down a bit. That's also a change in velocity, but this time it's a negative acceleration. See? It works both ways.
Now, keeping track of all these different numbers, position, time, velocity, acceleration, it can get a little complicated. But what if I told you there's a way to see a whole journey in a single picture? Well, there is, and it's something we're all familiar with, a simple graph. A distance-time graph is basically a storybook of a journey. If you see a perfectly straight, sloping line, that means our object is moving at a steady, constant speed. But if you see that line start to curve upwards, whoa, that means our object is accelerating. It's picking up speed. The shape of the line tells you the entire story at a glance.
And here's where it gets really cool. These graphs aren't just pretty pictures, they're powerful tools. If you have a velocity time graph, you can actually calculate the total distance an object traveled just by finding the area underneath the line on the graph. It's like a hidden calculator, built right into the visual. How cool is that? Okay, deep breath. We've learned the basic language of motion, things like displacement, velocity, and acceleration. We've even learned how to draw its picture. Now it's time to put it all together. It's time to unlock the real power of physics, the equations that let us predict the future. Don't let the letters scare you. These 3 equations are like the secret code to understanding motion. They are incredibly powerful. With these, if you know a few things about an object's journey, you can calculate everything else. You can figure out a car's stopping distance, the path of a thrown ball, even where a rocket will be in 10 seconds. They are basically a crystal ball for anything that moves.
So, we started with a simple question about whether your walls are moving, and we ended up here with the tools to describe pretty much any motion in the universe. From a leaf falling from a tree to a planet orbiting a star, you now have the fundamental language to understand it. The world around you is constantly in motion, and now you can see it with a whole new set of eyes. So, what are you going to see differently?